Here we show a video of a scene playing at 30 frames per second. If we want to know what goes on over a longer period of time, we can make a time-lapse video. But to do that, we need to choose a frame rate. Here we play the video at 256x. Longer-term motion becomes apparent now. The shadow and the clock can be seen moving, and towards the end we see some clouds drifting by. But now, the people walking through the scene are aliased, creating a distracting flickering artifact. We can speed up the scene even more to 1024x to make the motion of the shadow and the clock more obvious, but it would be better if we could show all of these things at a natural speed at once. Ideally, we'd see clouds moving at 256x, the shadow and the clock moving at 1024x, and the people moving in real time. In this paper, we present a method to visualize motion at multiple timescales in a single video, such as this. We start by taking a video at 30 or more frames per second for a number of hours. Then we construct a temporal pyramid by repeatedly averaging frames and speeding up the video. The frame averaging allows moving objects like people to blur out at higher levels of the pyramid. Then we pick a set of clips from different timescales. To combine all three of these timescales, we solve a labeling problem. For each voxel in the output video, we simply choose which input video its value should come from. Here we've color-coded the inputs and show the composite labeling in the bottom right. To decide on a good labeling, we use optical flow and feature tracking to detect the speed of motion in each input. Our goal is to normalize pixel space velocity so that all changes, regardless of timescale, are easy to observe. We call this motion normalization. Motion estimation can be noisy, and combining timescales can cause unnatural-looking seams. To ensure a smooth-looking output, we use graph cuts. The data term of the energy function is based on flow and tracks, and the smoothness term encourages the labeling to place seams where they'll be least noticeable. Here's the output created from this labeling. After a gradient domain blending step, here's the result. There may be multiple good ways to combine timescales. To allow for artistic control over the output, we allow a user to specify additional constraints on the optimization. Here, a user makes an annotation to ensure the more distant people are still included at real time, even though they're moving slowly in pixel space. The updated result with this new constraint is shown here. Notice the difference in the highlighted region between the automatic version and the annotated version. For each result, we'll show the output first. Then we'll show a tinted version to illustrate the timescales involved. Solid colors indicate annotations. Then we'll show the result once again. The slope dataset is a good example of how the user annotations can provide artistic control. Here we've made some annotations to ensure that the wispy clouds appear throughout the clip. But an artist might also decide that the other sky is more interesting. After 10 or 15 seconds with a large annotation brush, we can constrain the sky to come from a faster timescale. We captured this dataset at 120 frames per second, so the water's motion is actually being slowed down while the cloud's motion is being sped up. The pedestrian on the bridge appears in real time. Then a few seconds later, his slow-motion counterpart also appears. We'll show several more results here. Full results, including automatic results for all datasets, as well as an annotation example for each dataset, are included in the supplemental.